Have you ever found yourself needing to find the absolute steepest, fastest path up a hill? Or maybe figure out the direction heat will flow the quickest from a hot surface? Well, today we're going to break down the one mathematical tool that does exactly that. It's called the gradient. Let's get right into it.
See, at its very core, the gradient answers a really physical, super intuitive question. Which way is up? And not just any up, but the steepest possible path of change. Just imagine you're standing on a hillside. Maybe it's a bit foggy. You know the peak is up there somewhere, and you want to find the quickest, most direct route. Which direction do you take your very next step? You're looking for that one single direction that is the absolute steepest path up. So, how do you find it? And here is the key insight. This whole hiking problem, it's the exact same question we ask as engineers and physicists all the time. Whether we're talking about altitude on a hill, temperature flowing from a heater, or electric potential in a circuit, we're always looking for the direction of the steepest, fastest increase. So how do we actually solve this? Well, we need a tool, right? We need a kind of mathematical compass that, well, it doesn't point north. It points in the direction of steepest up. And that compass, my friends, is the gradient. Now, to really understand the gradient, you first have to be able to visualize the hill, or what we call a scalar field. The easiest way is to think of it like a topographical map. Every single point in space has a value assigned to it. It could be altitude, temperature, pressure, you name it. And the contour lines you see on this map, they just connect all the points that have the very same value.
Okay, so let's make it official. The gradient of a scalar field, and you'll see it written as grad V or with this upside-down triangle symbol, is a vector. That is the most important part to remember. It's not just a number, it has a direction. Its direction points you straight up the steepest path, and its length or magnitude tells you exactly how steep that path is. These three properties right here, they're everything. Number one, the vector's length is the steepness. Two, its direction points straight uphill. And three, and this is the really cool part, the gradient vector is always perpendicular to the contour lines. Now, why is that? Well, think about it. If you were to move even a tiny bit along a contour line, your elevation wouldn't change at all, right? The rate of change is zero. So to get the absolute maximum change, you have to move at a perfect right angle to it. All right, so I think the concept is locked in. But how do we actually calculate this steepness compass of ours? For that, we're going to need to look at the formulas. So the symbol we use for the gradient is called the del operator, or sometimes nabla. It's that upside-down triangle. You can think of it as a special kind of vector that's made up of partial derivative instructions for each coordinate direction. Now, by itself, it doesn't really do anything. But when you apply it to a scalar field, it magically gives you that gradient vector we've been talking about. And here are the recipes. These are the formulas for our three main coordinate systems. For the standard XYZ system, that's Cartesian, you can see it's a really straightforward set of partial derivatives. Now, for cylindrical and spherical coordinates, the geometry just adds a few extra terms. You don't need to memorize these right now. Just know that the right recipe always depends on the shape of your problem. Okay, enough theory. The best way to really get this stuff is to see it in action. So let's take an example directly from our source material and calculate a gradient step by step. Here is our scalar field V. We're going to find its gradient by simply following the Cartesian recipe. That means we'll find the partial derivative for the x direction, then the y, and then the z. Let's just take it one piece at a time. First up, the x component. Now, the absolute key to partial derivatives is to treat every other variable as if it's just a constant number. So for this step, we only focus on the sine of 2x. Its derivative is 2 times the cosine of 2x. And all the other terms, they just come along for the ride. Easy enough. All right, now for y. We do the exact same thing. We just ignore the x and z terms for a moment and focus only on the hyperbolic cosine of y, or cosh y. Its derivative is sinh y. And boom, that's the second piece of our vector. And finally, for z, we're going to treat x and y as constants. The derivatives of e to the minus 2z is minus 2 times e to the minus 2z. And that gives us our third and final component. Now we just assemble the pieces. We take each component we found, attach its proper unit vector, ax, ay, and az, and then we add them all up. And that is our gradient vector. At any point in space, this formula right here will give you a vector that points in the direction of the steepest ascent for our field V. Pretty cool, huh? Okay, I want to make a quick but really critical clarification. The gradient always points you to the steepest path. But what if you don't want to go up the steepest path? What if you want to know the slope in some other random direction?
This is a classic point of confusion. What's the difference between the gradient and something called the directional derivative? Well, this slide lays it out perfectly. The gradient, that's a vector pointing you to the steepest path. Period. The directional derivative, on the other hand, is a scalar. It's just a number that tells you the slope or rate of change in any specific direction you choose, not just the steepest one. It's like asking, hey, what's the slope if I walk northeast? Instead of asking, where is the absolute steepest slope from where I'm standing?
Wow, okay, we've gone from a simple hill all the way to some pretty serious calculus. If you only take away 3 things from all of this, please make it these 3. 1. Direction. It points straight up the hill, always in the direction of the fastest increase. 2. Magnitude. Its length tells you exactly how steep that hill is. And 3. Perpendicularity. Remember, it always cuts across those contour lines at a perfect right angle. You master these 3, and you've absolutely mastered the concept of the gradient. Seriously, from optimizing machine learning algorithms to mapping electric fields, or even figuring out how heat flows through an engine block, the gradient is absolutely everywhere. It is the fundamental tool for finding the path of maximum change. So the only real question left is, what will you use it for?